get started with the second part. What we've shown is that the total momentum of the system will be changed by external impulse. This means that as long as there's no external force acting on the system, then the impulse on the system will be zero, and the momentum of the system is conserved. The system can have some internal force going around, but as long as there's no external force acting on the system, then the momentum of the system is conserved. So if we have a frictionless table and a ball is coming in with initial momentum, going to hit another ball. So the first ball has initial momentum, and the second ball has zero initial momentum. Okay? Now, if there's no friction on the table, and the ball is not going to fly away from the table, so the gravity and normal force from the table is cancelled, then the momentum of the system will be conserved. Now, momentum is a vector. It has direction, or it has two components. So if the momentum is conserved, the vertical momentum is conserved, so does the horizontal component. After you collide the balls, the first ball might fly toward this direction. This is the final momentum of the first ball. And for the second ball, should the horizontal component of the second ball's final momentum go to the right or left? Let's look at the initial state. So initially, the first ball has a momentum going up. So the horizontal component of its momentum is 0, good. And the second ball has 0 momentum. So the momentum of the system is vertical. The total momentum only goes in a vertical direction, and the horizontal momentum of the system is 0. So if momentum is conserved, the horizontal momentum in the final state should also be 0. Now, if the first ball goes to that direction, which direction of the horizontal component should be on the second ball? To this way, right? Because the horizontal component of momentum is conserved, the final momentum of the ball must have horizontal component in opposite direction, and it will be equal and opposite such that they sum up to 0. So what you see is that the vertical component is conserved because at the end they are both going vertically up, and the horizontal component is also conserved. The horizontal component of the final state is down to 0, which is the same as the initial component, initial momentum. Okay? So momentum is a vector. Momentum conservation is writing two equations at the same time. The x momentum is conserved, and the y momentum is conserved. So let's say the initial momentum of the first ball is 10 vertical. Let's do x and y. Let's say it is meter. It is kilogram, meter per second. And we see that the final momentum of the first ball is -3 plus 5j. Okay? So if momentum is conserved, what should be the final momentum of the second particle? What would be the I component? Good. 3 and -3 need to sum out to 0. I didn't write the x component of the initial momentum because it's 0. How about the y component?
5.
Good. 5 and 5 need to add up to the same as the initial y component. Okay? So you see momentum conservation is a lot easier than F equals ma. If you use F equals ma, you need to know how the force behave, and you need to calculate acceleration. Use that to get the area under VT curve to get the final position. Conservation law is a lot easier. Let's look at another example. Let's look at how rockets work. So a rocket usually flies in space. In space, there's nothing it can drag onto, it's empty. It cannot just drag itself against the table to move forward. That's not doable in space. So the way rocket propels itself is by momentum conservation. Let's say initially the rocket is not moving, so the momentum of the initial state is 0. What the rocket has is some fuel inside it. And if it is inside the rocket, then its initial momentum is also 0. Okay? What the rocket will do is to eject the fuel in the opposite direction that it wants to fly. So the fuel will have a final momentum. Now, momentum is conserved because in space there's no force acting on the rocket. Space is empty. So if momentum is conserved and initially the momentum is 0, then which direction should the momentum of the rocket be in the final state? Going to the right, right? The final momentum of the rocket must be equal and opposite to the final momentum of the field, so that the momentum is down to 0, which is the same as initial momentum. So that's how a rocket works. We have some rocket. We can play around with the rocket. So I'm going to pump as much as I can. I am pumping as much as I can. And here's how rocket works. Okay? So you see, even though I try to pump a lot of air, it flies like this, which is not so useful. It is because it is air. If you try to blow air, it has a speed limit. No matter how hard you try to pump the rocket, the air that comes out from behind cannot exceed the speed of sound. The maximum speed you can excel, like can push out the air is the speed of sound. And it's not going to reach the speed of sound. It's not that easy. So if you only have air inside the rocket, then the momentum of the air in the final state, which is the mass of the air times the velocity of the air, will be small. The speed of the air, or the velocity of the air in the final state is limited. On inertia, of course, because there's air around the back of the rocket. If the rocket tries to push the air back, the air that it pushed out will run into the air outside the rocket, and the velocity of the air cannot go that fast. What we can try to do is to increase the mass of the fuel to increase the final momentum. That's why we have water in here. Water has bigger density than air. It's 1,000 times bigger. And by using water as our fuel, we can push out the water as fast as the air and get a big final momentum on the fuel. So let's see how it looks like. Alright, I don't think I can pump even more. So this is what it looks like with water. Can you guys see that the final momentum of the rocket is much bigger than the first try, which we only have air. This is because momentum is proportional to mass. The bigger the mass, the bigger the momentum. So if I use water as fuel and push it out with the same velocity as I push out the air, the rocket will get a bigger final momentum. Okay? So the way we discuss momentum conservation so far is by looking at situations which external force is zero. But what changes momentum is not force. What changes momentum is impulse. And impulse is force times the time interval. So as long as the product between these two is small, momentum of the system is conserved.